All right.
Wait. How many? Is it 10 by 10 graphs?
It's a 10 by 10. That's right. So our goal here is to sketch f prime based upon f. And I want to caution you ahead of time, do not try to make f prime look like f, because it is exceedingly rare that that would actually happen.
When would that happen?
There's one famous function that we will encounter later whose derivative is itself.
Here now.
Nope.
What?
Something to do with
I gotta give you some reason to keep coming to class.
something to do with E, I bet.
All right.
No.
So what is the right way to visualize this? The right way to visualize this is to remember that at all times f prime is the slope of the curve. And if that's not enough for you, that is the same thing as the slope of the line tangent to the curve at each point. So now with that in mind, I notice that this particular graph right here is divided up into 4 pieces, right? And it would make sense then that I could evaluate the derivative for each of the 4 pieces separately. Let's start with the first piece right here. This piece is a straight line. What do you know about straight lines? They have constant slope. What is the slope of this line? That's not too hard to figure. Let's count it. We've got 3 up, and we've got 1, 2, 3, 4, 5, 6, 7. So a little bit less than 1 over 2 is my slope right here. So this slope is 3/7. Positive or negative? Positive, because the line's going up here. Because this is a straight line, my slope will therefore be constant over the entire interval. The value of my derivative is going to be 3/7 all the way across until I hit the sharp corner right at x equals -3.
Why is that in the negative x? I mean negative y?
Because I should have drawn it up here. Here we go. Thank you. I sort of picked an arbitrary starting point. So I want you to observe the following things about my derivative, f prime. First thing, for a straight line, f prime will be a constant, a horizontal line of some value. Second thing to observe is that the value of the derivative, 3/7, is the slope of the curve f. So that as my curve changes in slope, then the value of the derivative is going to go up and down with it. Okay, second piece. Again, a straight line. What is the slope of this straight line? -2/3. And you can just go ahead and write slopes right there just to remind you of what's going on. And so I'm going to take the value of the derivative to be -2/3 here. What happens at the joint where they come together? We actually already know the answer to that question. Because my derivative from the left is 3/7 and my derivative from the right is -2/3, therefore my function will be non-differentiable right here. F prime will not exist, and I will have 2 open circles reflecting a jump discontinuity in the graph of f, because my slope immediately, instantaneously changes from 3/7 down to -2/3, right at x equals -3.
Wait, I'm confused now.
Okay?
So because there's a corner, it's not differentiable. Because it's not differentiable, there are 2 poles and the 2 are connected.
Let's do all that again, but I want to abolish the word it, because we now have 2 its on the table. We've got f and we've got f prime. Because f has a corner, f is not differentiable at x equals -3.
I guess that's why are the lines like horizontal? Why do you make them horizontal?
Aha! This is the visualization thing. Because f has a constant slope on the entire interval from -3 to 0, therefore f prime, which is the slope,
Oh, it's horizontal.
has a constant value from -3 to 0.
Okay.
Okay.
Yeah, I guess.
Yeah. This is part of the learning process. She's doing it right. She's thinking it through. Does everybody understand her question and the answer to it? Sue, I'm not sure. Talk to me. Which part don't you like about this? Okay? First, let me ask about the corner right here. Does it make sense to you that the sharp corner right here, where the derivative from the left is 3/7 and the derivative from the right is -2/3, means that f prime will have a jump in its value right here? Okay? Second thing, does it make sense to you that a line has a constant slope and therefore its derivative has to be a constant value? Okay? Then that's kind of all that we have to see at this point. In terms of visualization, any straight line function f will have a constant slope f prime. That's it. Moving on to this, and I'll come back to Joseph's thing. What is the slope of this segment right here? 0. The slope is 0, therefore my derivative is 0, all the way out to here. And then finally, what's the slope of this line roughly? -1, and therefore my derivative is going to jump down to -1. And right at the endpoints, we're going to assign the value of the derivative to be the derivative from the appropriate side. So we're going to have filled in dots here and here for our derivatives there. So this is our f prime for the f, and I can read it backwards to check myself. Here's how I check it. What this is telling me is that my curve has a slope of 3/7 for the entire portion from -10 to -3. Is that true? Yes. This is telling me that my curve has a slope of about -2/3 for the entire portion from -3 to 0. Is that true? Yes. Slope of 0? Yes. Slope of -1? Yes. And so everything checks out.
I get it. We could just say this.
What's that?
Oh.
Okay.
Wait, so just to make sure I'm getting this right, so if f of x was a was like, for example, in quadratic function, then the derivative would be a line, like a linear function?
Yeah. Well,
Okay.
But it would touch the point, correct? Like the quadratic.
yeah, let's actually go back to the graph that we started with today, right here, and let's actually sketch an f prime for this guy. I'm going to clear out all the tangent lines that we drew. Okay, and now what we're going to do is we're going to sketch the graph of f prime based on this. What I want you to observe about my f of x right here is that my f of x is no longer a set of straight lines. It's no longer piecewise linear. And because of that, I do not expect constant slope. My derivatives are not going to be horizontal lines. Instead, they are going to be changing. But the second thing I want you to observe is that my curve is a smooth curve. It has no sharp corners. It has no cusps. It has no vertical tangents, and therefore I expect that the derivative will exist for every single point throughout. So how am I going to sketch that? What I'm going to do to sketch f prime is I'm going to go on this curve and find the easiest points first. And the easiest points are the places where f prime is equal to 0. And we already found those places. Those places that are at x equals -3 and x equals +3, right? So I'm going to mark those two places on my graph of f prime as zeros because that's where the slope is actually equal to 0. Notice that it happens to coincide with the value of f here. That's purely coincidence. Okay? Then I'm going to go to the places where the curve is the slopiest. And that is here, as we saw, like that, and here. And the reason that I'm going to go to the places where the curve is the slopiest is that these are going to give me my max and min values for the derivative. And it looks to me as if the slope right here is over 2 and a little and up 3 and a little, so my slope is about positive 1.5. Notice that this is a rough approximation right here for the slope at this point. And so to mark that, I'm going to go to this point right here and mark that maximum slope. And all in between, I'm going to make the slope positive and a smooth curve. So my rough graph of f prime goes from 0 to 0 up to 1.5, and I just make it a smooth curve throughout. Will those values on the smooth curve exactly be equal to the slopes? No, this is just a sketch. That's okay. Let me finish this and then I'll take your question. Likewise, I'm going to go over to this point, which is where my curve is the slopiest in the negative direction, and I'm going to find the slope here. It's over 2 and down 4 and a little. So I've got a slope of about -2, something like that at this point, and I'll go down to -2 right here, and I'll make my curve, my derivative, a smooth graph to here. Notice that my slope does not come back to 0 on this side because my curve doesn't have any horizontal tangent on that side. And then finally, over here, I'm going to get one estimate. It looks to me like my curve is the slopiest right at the end, right? And so that gives me a value of about, I don't know, -2, something like that. And therefore, I'm going to go down to -2 by the end right here. And here's my sketch of f prime, and that's it. So let's go back through how we got all of that, because Alina was going, wow. We got all that by sketching a framework for ourselves, first of all using the horizontal tangents, then using the steepest parts of the curve. And once I knew the points that were horizontal tangents, those give me zeros in the derivative automatically. And once I know the steepest parts of the curve, those give me maximum and minimum values for the derivative, and then I just connect the dots with a smooth curve.
Wait, how did you find the minimum value?
I found the minimum value by going to where the curve was the slopiest.
Can you find the slope?
Yes, because the derivative is the slope of f. Yes.
How do you find this, or like where it goes out in between the zeros?
Here?
Yeah.
Yep. I got the zeros, and then I went to the steepest portion of f, drew that tangent line, found its slope, found a value of 1.5 for that slope, and marked the 1.5 at the matching point there. And then I just did connect the dots. Okay, Peter, you had a question?
Yeah, I was wondering when you had, let's say, the full f prime and you're trying to graph it, let's say you have 0 and you have 2 or 1, or 1.5, let's say that, and you graph it like this, right? How do you know it wouldn't look like this?
Great question. Peter's question is, all that I really had were these 3 points. How come I knew that the f prime didn't do something crazy like that? Maybe that's your question. And the answer is, at this point, I don't necessarily know, except to tell you that your curves should look like simple smooth curves, and this is pretty complicated behavior right now.
Okay.
Okay?
I'm not saying like
There'll be a better answer later,
okay.
but right now I'll just say keep it simple.
Yeah. I mean, it's kind of intuitive, but I'm not like.
Yeah. At this point, it would just be intuitive. But that's a good question. Yes, sir.
When you're designing the derivative, how do you figure the outer parts again?
Okay, yep. So the zeros are clear, right?
Yep.
And then to get these 3 points, here, here, and here, I went to the steepest parts of the curve and found slopes based on those.
Okay.
Yep. And these 5 points, the 2 zeros and the 3 maxes and mins, were enough to get the whole thing.
So when you found the steepest derivatives, then you used the slope as like the y value.
Yes. The same point where I had found that slope. So the point of tangency here was the x value. Good question. Let's do another one. Here, I'm going to have a semicircle. If I can. Apparently I can't because my artwork is, I'm artistically challenged. have a semicircle. Behold, a semi-egg. All right. And now what I'd like to know is what does f prime look like? Okay, well we kind of know how to do this. We're going to start by finding the places where f prime has what value? 0. So I'm going to start with f prime equals 0. And where is the location where f prime is equal to 0? When x is equal to 0. There it is. And so that gives me a 0 for my derivative. Next thing. I'm going to go to places where the curve is the steepest. Where is the curve the steepest? At the endpoints. Now I have something really interesting that I didn't have with the other curve. What's true about my tangent line at the endpoint?
Vertical.
It's vertical. Watch those vertical tangents, because a vertical tangent means an infinite derivative. Huh, how do I do that? I'm going to do that with a vertical asymptote in my derivative. So f prime is going to have a vertical asymptote. I can say it like this. F prime of -4 is equal to, let's see, is it positive or negative infinity?
Positive.
Go next door and look at those slopes. So we're looking at positive or negative slopes here? Positive. So as I work back, I'm looking at positive infinity. And how about f prime of +4? You fall off the world on the other end. And therefore, I'm going to take my derivative all the way out to positive infinity. And then I'm going to take it all the way out to negative infinity down here. And I just connect through with a smooth curve.
So you know how, sorry, you know how, enough from the class. So, you know how it goes like this, and how sometimes when you get the vertical tangent, it can then carry on.
Yes.
How would you necessarily do the rest of that carry on part after on the left side?
Let's do that. Let's take our classic example function for vertical tangent, which is the cube root of x. And it goes, let's see, 8, 2. So here's my cube root of x right here. And right at x equals 0, it goes vertical. Okay? And so now we want f prime. So I first look for any places where I have horizontal tangents, and although my tangents are getting small here, they're still not quite horizontal, so I have none of those. And then I observe that I have a vertical tangent right there at x equals 0. And I observe that that's going to be a positive infinity because my curves are like that. So immediately on my graph of f prime, I'm going to draw a vertical asymptote for my infinite derivative. And because my derivative is positively infinite on both sides, therefore my derivative has to be positively infinite on both sides. And now I can also observe that as my curve goes out, its slope gets flatter and flatter, so that I'm going to draw the slope approaching 0, but never quite getting it. And so there's the graph of my derivative. It has positively infinite values on both sides because my original f has positively infinite slope on both sides. And it goes down to 0. Yes, sir. Jack's question. Okay. Yeah.
Would cusps kind of go like this? And
Yep.
carry on?
Exactly it. Sure can. Big. Gotcha. Yes, sir.
Questions like these, do they like tell you what f of x is equal to like here to?
No, actually.
Okay, so basically trying to like estimate kind of.
Oh yeah, it's very much a rough estimate.
Otherwise, you just use polar or just kind of
Right.
go,
Here's one place, they don't do this as much anymore, but in chemistry they used to do this kind of sketching because you would do a procedure called a titration. Have you guys done titrations? Some of you have? Okay. And in the titration, you look at the pH as it drops or as it increases based on what you're adding to what. And at some point, your curve goes vertical, right at what's called the end point of the titration. And so the right way to find that endpoint of the titration is to sketch f prime and look for that peak where the slope becomes infinite. Yes, sir.
Actually, can you bring it back to
Uh-huh. And then I'll do one more before the bell rings.
Will we ever have to, since graphs aren't like the best of evidence, will we ever have to be told, all right, here's a graph, do f prime and tell us what the equation is?
I might, but that would be probably self-defeating in as much as if I tell you what the equation is, then poof, calculator, and there it is.
On a non-calculator then?
Yeah. Okay. Now, I want to take our smooth curves and our straight lines and put them together in the same kind of a function. So let's say we have a function that goes like so. And then it goes like so and so. And now the question is, here's my awful looking f of x. What does f prime look like? So I'm going to do exactly the same reasoning. I'm going to begin by finding places where f prime is 0. And clearly f prime is 0 right up here at the top. So I will go down in my graph of f prime and I will put a 0 for that horizontal tangent. Everybody's with me so far? And I also notice that f prime is 0 for this entire interval, all the way from x equals 2 all the way out to x equals 10, because we have a horizontal line. Okay? Now it's just kind of a matter of which one do I want to do first. Do I want to do the straight line segment first or the smooth curve? Straight line. Love it. So the slope of my straight line looks like it's going to be negative 3 over 2. And therefore, for this portion, I'm going to draw myself a horizontal line with a value of negative 3 over 2. I'm going to have a a jump right here where there's a sharp corner in the graph. And there's also a sharp corner right here because the derivative from the right is negative 3 over 2. The derivative from the left looks like it's more like negative a quarter or so. Everybody see what I'm saying? Now I come back to my smooth curve and I look for the steepest parts. It looks like the steepest part is right over here. And that steepest part looks like it has a slope of about 1.5 or 2, something like that. So I'm going to make the value right at this point of tangency be about 1.5 or 2.
Isn't that a vertical?
That's a tough call. Does it actually go vertical or does it just kind of slope in like that? To me, it looked like it sloped in like that. On an actual question, I will tell you if there are vertical tangents. So you won't have to guess. Because otherwise you'd be going, well, is my slope just a really large number or is it actually infinite? And you couldn't know in the graph necessarily. And then over on this side, it looks like my steepest part is maybe right here. And it looks like I have a slope of about negative, I don't know, negative 0.75, negative 3/4, something like that maybe. Hard to tell. So negative 3/4 right at this point, like that. And then it goes all the way down to about negative 1/4 right here. So my slope recovers to here. And now I'm just going to connect these dots with a smooth curve, and I'm done. Yes, sir.
How do you like graph a kind of like a quadratic like this?
Well, so since you already know what type of function it is, then you can do two things. You can graph it with the skills that I've given you, or you can graph it knowing what the function is. So because this is a quadratic function, I know ahead of time that its derivative is going to be a linear function.
Oh yeah. Then.
Or I can go and say, all right, I've got a derivative of 0 right there. So my f prime is going to go like that. And on this side, my f prime is going to be positive and getting more positive as we go. Therefore, my f prime needs to look like that. And on this side, my f prime is negative, but it's getting less negative as I head towards x equals 0. So my f prime has got to look like that.
But wouldn't it be like almost negative infinity on the graph?
It depends on how steep this goes, right?
Yeah, if it's really steep, then what happens?
Yeah,
Do you get mod this?
let me close this out.